Hello there. Welcome to this video. It is yet another video on the QPython package. And today we're talking about the uh, phase type distributions that you can use for the time to event distributions in Q. It's a special type of distribution. Today we're going to follow the documentation fairly closely because it has some nice diagrams and examples and notation for us to go from. So I'm just going to start at the beginning here. At the top, one particular subset of distributions offered by Q is phase type distributions, and that's what we're going to learn about in this particular video. Is what is a phase type distribution? These are very helpful and useful and versatile family of distributions defined by absorbing Markov chains. That is a given probability vector alpha representing the probability of being in some given starting state, and a transition rate matrix M of an absorbing Markov chain. These are distributions given by the time to absorption. It is therefore a random sum of exponential variables. The diagram below gives a general representation of an absorbing Markov chain with four states, 1, 2, 3, and not 4, but what we'll call the absorbing state or star. Now I'm going to pull that diagram out in another browser here just to get a sense of what's going on here. So one thing that's not in this diagram, but you first can see that this is a network diagram. But the first thing that's not in this diagram that we just heard about from that first paragraph is there's some probability of starting off in each of these states, 1, 2, and 3. And that's what these circles represent, being in a state. The arcs between them, or the arrows, if you will, represent state transitions, or the weights on those arcs represent the rate at which those state transitions occur. Okay, so if I start off, let's say, with some probability in state 3, I might go over and transition into state 1, and then back into state 3, and then into state 2, and then back all the way to state 1, and then to the absorbing state. That's just one of the possible histories. The cool thing about phase type distributions is that you're just sampling from a probability distribution that incorporates some chance of being in any of these initial nodes 1, 2, and 3, and how long it took to go through this network at whatever random probabilities until you finally reach this absorbing state. So it's a way of saying, let's sample how long something would stay inside of this network. And eventually it leaves in the sense of getting to the absorbing state. Okay, so let's jump into a little bit of the mathematical notation. We've got the corresponding phase type distribution would be defined by an initial state probability vector alpha, which is equal to P1, P2, P3, and 0. P1, P2, and P3 are respectively the probabilities of starting off in states 1, 2, and 3, and 0 is the probability of starting off in the absorption state. There's no point in saying how long it takes to get to the absorption state if you actually start in it. Now, the transition matrix corresponding to the absorbing Markov chain is written as M. You could use other symbols, of course. And you can see that there's this property here that along the diagonal is the rates of leaving that node. And the off diagonals there represent the rates going into the other nodes from that diagonal node. And an important property of these transition rate matrices is that row by row, the sum is 0. The last row there are all zeros, and that's to say that there's no leaving the absorption state, so there's no rate out. And so even on the diagonal, there's 0 rate out. Once you're in there, and there's nothing else to go. There's nowhere else to go. Okay, so I want to go ahead with following their little coded example, and we're going to sample from this distribution. I think I'm going to skip typing out the matrix here, and I'll just copy paste that code right in. And then we'll also initialize their example distribution here. So we're passing in phase type, or we're initializing a phase type, and we're passing in our initial state vector, which I put up here, of 0.7 probability of being in the first state initially, 0.2 probability of being in the second state, and 0.1 probability of starting off in the third state, and 0 probability of starting in the absorption state. In this example, they're calling it an absorbing matrix, but it's still just a transition rate matrix. We've got that leaving the first node, there's a rate of 6, but then going into node 2 is a rate of 2. No going into node 3 from node 1, and then there's a rate of 4 to go from node 1 into node 4. Now notice that the sum of these entries adds up to 0. -6 plus 2 plus 0 plus 4 is 0. And you can similarly interpret these other rows, including this final row of the 0, 0, 0, 0 that we talked about for the absorption state. Once you're in the absorption state, there's no going out of that state. Okay, good. So we throw in that initial state, and we throw in that absorbing matrix, and there's our probability distribution. Now I also want to include matplotlib. And let's actually prepare a sample of this distribution, where I'll go ph.sample for underscore in range, and let's just give this a generous sample size of 10,000. Now let's go PLT and make a histogram. We'll put in our sample, and then let's go for 100 bins. And then let's show the resulting plot. And you can see that this is the amount of, it's a histogram, it's a probability distribution over a non-negative variable. So just as a reminder, what this x-axis represents is the amount of time that, say, your customer or patient or whatever stayed in the whole network of states, in and among those 3 states, before reaching that final end state. It doesn't distinguish between the different states that the let's say, patient actually started in. Those happened each with some probability, but this is mixing all of those things together for you. So you get this probability distribution that looks like a rough kind of L shape, right? So the phase type distributions are a large family of distributions. Some phase type distributions have particular structures to their underlying absorption Markov chain, and that can be particularly useful. And Q offers helper classes for some of these to build the state transition matrix for you. In other words, it might be a bit of a chore to specify the absorbing matrix for every case, when maybe you know you're in a well-known case where the matrix has a particular form, and so you can pass in less extra parameters for how to build stuff yourself. Okay, so one of those examples is an Erlang distribution. And we're also going to look at the diagram that they've got there in just a moment. But first, let's read what they have to say about Erlang distributions. An Erlang distribution with parameters lambda and n is the sum of n exponential distributions with parameter lambda. So that is pretty much definitional. And if you work out the formal mathematics of taking literally n number of independent exponential random variables that have the same rate, and that independent part is actually kind of important and wasn't mentioned, but that makes the math really so much easier. Anyway, that's the case. This can be equivalently be defined as a phase type distribution with the following structure. In other words, phase type distributions are a generalization over many probability distributions that happens to include the Erlang. So what is this like from a diagrammatic point of view, just like the network diagram we had before? So we got states 1, 2, 3 all the way up until n, and then we've got this absorbing state. So this is like a process where the patient has to start off in the very first state, and with some rate lambda they go to the second state, and then with some rate lambda they go to the third state, on and on and on until they get to the nth state, and then again at the same rate lambda they exit. They leave that system, basically, whatever that process is. So that's when there's just simply a sequence of steps that are all the same, and there's n of them, that there's going to be some amount of time that it takes to go from 1 all the way to being done. Great. So hopefully you can see how that's a special case of phase type distributions. You can see that you've got the rates, you've got some kind of network model, and it's just a sequence in this case of exponential time steps. Okay, so the corresponding phase type distribution would be defined as an initial state vector with alpha being 1 and everything being 0. Because remember I said when I was showing you the diagram, you start off at the first node. It's not obvious or apparent from the diagram. You do need to keep in mind that you could create another phase type distribution with the same diagram, but you can start in different nodes. That would be a different system, but you can do that with phase type as well. So anyway, here's the transition matrix, and you can see that it's got a whole bunch of zeros, and then a pattern emerges here where you've got diagonals are minus lambda until you get to the end, which is the absorbing state, that's 0. And then just the off diagonal to the next node to the right is plus lambda. And that gives you your minus lambda plus lambda is 0. So that satisfies the rate transition property. And this would be kind of an annoying matrix to write out. You, of course, could write code yourself to make this matrix, but one of the ideas with having these additional implementations in Q is that you don't have to write them out yourself. So for an Erlang, we can just copy this. You only need to provide certain pieces of information, right? Because all of the rates are the same. So you've got a rate of 9. Notice that we didn't include the initial state probability vector, and that's because it's the same one every time, given that you know how many steps there are. So in this case, 1, and then with the number of phases being really the number of those states to go through is 4. You know that it's going to be 1 followed by 3 zeros for the other states, and then another 0 for the absorption. Do I have that right? Or maybe there's one more because of the n+1 edges. That might be right. Anyways, it'll put together this matrix for you behind the scenes so that you don't have to define this matrix yourself. Now, likewise, I would like to take a sample. I think the documentation could probably be improved here, because if I remember right, a lot of the distributions are quite similar looking, but there are ways of making distributions that are very different looking, so maybe we'll create that sometime. So this just looks like a gamma distribution. I should rephrase what I just said. To me, none of the distributions look highly surprising. The thing I'd really like to create an example of later is like bimodality, which should also be approximated as some type of set of phase type distributions. All of the examples are unimodal, or they're like the exponential or gamma distributions. So anyway, suffice to say, this is an Erlang distribution. It's quintessentially the probability distribution that you get from adding a collection of independent and identical exponential random variables together. And this is the amount of time. So it's non-negative, and you get this tail, and there's a most likely value, but you're starting to see not the full CLT, not the full central limit theorem, because this does, it is only a sample size of n, which can be small. But you shouldn't be surprised if this starts looking more and more like a normal distribution as you add a very large number of n together. Okay, next distribution that's a special case of the phase type distribution is the hyperexponential distribution. A hyperexponential distribution is defined by a probability vector, p again, and a rate vector, lambda, and samples an exponential distribution with parameter lambda sub I and probability sub I. This can be equivalently defined as the phase type distribution with the following structure. Let's take a look at that, because I think that the picture is going to be much clearer than the worded description here. So in this diagram, we actually have included the probabilities. We got P1, P2, P3, all the way up until Pn of entering into any of these 1, 2, 3, or all the way up to n states. You could start off in any of them. Notice that there are no arcs going between any of the 1 through n states. They all point to the absorption state in this. And this is really a way of saying you're going to have a mixture of not gamma, well, technically special case, but a mixture of exponential distributions. So it's like saying with some probability p subscript whatever, you're going to be in one of these states, and then at some rate you'll finish service. So it's really a network representation of a mixture of exponentials with possibly and usually distinct rates, which is different than the last example. We assumed that all the rates are the same. Here the rates can be distinct. And here we can have probabilities of starting in any of these states. Okay, hopefully that's clarifying. So when we've got this vector p, which is p1 through pn, and lambda, which is lambda 1 through lambda n, the corresponding phase type distribution would be defined by an initial state probability vector of alpha with p1 through pn and 0 for the absorption state. And the transition matrix is encoded differently than what we saw in the last one, right? The last one we had just the off diagonal where the values went. This one, we've still got the negative rates coming out of the states until the absorption state at the end. But for the final place, that the rates are going out from those nodes to are all the absorption states. So we've got this final column is lambda 1 through lambda n. Now, rather than define these in Q, we create a hyper-exponential distribution from the parameters lambda vector and probability vector. Great. Let's take a look. So, just the same as what we were looking at before of it's just available in the distribution submodule. Here we have to pass in our distinct rates, in this case 4 of them, and we have to give these probabilities for entering into each of the 4 possible states. And remember, those rates are only for going to the terminating state. Let's take another sample. And let's plot histogram. So this distribution, I'd say, is a bit thicker tailed in the sense that while it drops down very quickly, you can see that these values go out further. There's a bit of sparsity going on, but that's common with sampling longer tail behavior. Technically, this isn't a long tail distribution if you know about that whole hierarchy, but it's a distribution that's relatively longer tailed. Okay, next. Hyper-Erlang distribution. So if you remember the names we got before, Erlang came from summation of exponentials. Hyper-exponential came from mixtures of exponentials. Hyper-Erlang, you should be thinking this is going to be a bit of both. It's going to be a bit of summation and mixtures. Let's read the thing and then we'll look at the diagram. So a hyper-Erlang distribution is defined by parameters lambda, p, and n, and samples an Erlang distribution of size n sub I with parameter lambda sub I with probability p sub I. This can equivalently be defined as a phase type distribution with the following structure. Okay, let's look at the diagram because, again, I think that's much more clarifying for us. Certainly is for me. I zoom out anymore. It's going to let me zoom out any more than that. Okay, well, we've got, we'll scroll, right? Yeah, okay, great. So here we've got these channels P1 through PM, and this is really saying that there's some probability of entering into one of these M different separate sequences. But these are sequences just like we saw with the Erlang, where you've got these sums, and within each of these lanes, the rate is the same. So lambda M, on and on until you get to this state M, N subscript M. And then with some rate, again, still lambda M, you go to the absorbing state. Or if I go up to the top here, if I, with some probability, p sub 1 entered this lane first, and we've got 1, 1, we would go to the state 1, 2 at a rate of lambda 1, and then to 1, 3 with a rate of lambda 1, on and on. So within these lanes, it's Erlang type of behavior, but we're getting this probability mixture of M number of such lanes. So it is a mixture of Erlang distributions. That's pretty nice for saying, what if there's a bunch of different trajectories that a patient could take, that if you're in one trajectory, you're never going to cross over into one of the other ones. It's a distinct thing that's been identified, and that there's eventually some end. Okay, so when P is equal to a half, a quarter, and a half, and lambda is equal to 5, 2, 3, and the ends are, because that's the length of how long each lane is 2, 1, 2. The corresponding phase type distribution would be defined by an initial state probability vector of alpha is equal to 0.5, 0, 0.5, 0.5, 0, 0. Okay, so then we'd also have this transition rate matrix of -5, cancels with the 5, -5, cancels with the 5, -2, and 2. Oh, interesting. Yep, no, my brain just did a double take there. Of course, that adds up to 0. And then -3 and 3, and then -3 and 3, and then 0. Okay, so rather than define these again, there's a probability distribution available so that we can have our mixture of Erlangs, or hyper-Erlang. So again, it's available in the distributions submodule. We got to pass in the rates we want. We need to pass in the probabilities of entering each of those lanes that we want. And we need to pass in the phase lengths, or that's again like how long each of those lanes or trajectories were. And again, let's take a sample and let's take a look at a plot. It's another pretty long-tailed distribution where you can see that it's got a bit of undersampling in the tail there, which is common. And that this, again, to me looks like another fairly boring L-shaped distribution, but hey, they're pretty common. It's just the way it is. Okay, I think this is the last distribution we're going to cover in this video, which is another special case of the phase type distribution called the Coxian distribution. I think that's because there's a statistician whose last name is Cox, Cox. A Coxian distribution is defined by parameters lambda, the rates of each phase, and the probability vector p, the probability of going into the absorbing state after each phase. This can be equivalently be defined as a phase type distribution with the following structure. Again, we're going to look at the structure to hopefully clarify our thinking on this. This one's kind of interesting. It is a sequence of states, 1 that goes to 2, that goes to 3, etc., that goes to n. The rates are not the same, and we've got these side probabilities of, if I've got p sub 1 minus p1 of going from 1 to 2, there's correspondingly a probability p1 times the rate lambda 1 of going to the absorption state, and same for 2 versus going to 3, and the same for 3 going to the absorption state versus going on to 4 or 5 or whatever all the way to n. So what is this like? This is like a process that's like running a gauntlet, where maybe you're trying to run from step 1 to step 2 to step 3, but there's some chance of failure. If you've ever seen people running obstacle courses, maybe you're at step 1, you pass the first challenge, so you go to step 2, or maybe you fail the first step and you've left the system, the absorption state. Or you manage to get to step 2, and maybe you fail there and go to the absorption state, and maybe not. Maybe you continue on to the third challenge, on and on. So it's like a Coxian distribution is like having an obstacle course that you're trying to run, and you may or may not get to the end. Eventually you get to the end state anyway, because you have to have that defined, but you might leave that sequence sooner. Okay, so in this case, for the parameters, when p is equal to p1 through pn and lambda is equal to lambda 1 through lambda n, the corresponding phase type distribution would be defined by an initial state probability vector. Alpha is 1 followed by a bunch of zeros for all of the other states, and then the absorption state as well. So this is one of those examples where you definitely start off at the start of a sequence. You don't just jump into different parts. But you know what? With the general phase type distributions, you absolutely could. The idea of having these additional special cases is to say these are known cases that you might want to use. It's not to box yourself into saying you have to use these. But when you want, you'll have to step back to designing your rate transition matrix to solve the problem you want, and similarly to set up the initial probabilities for where you want things to start off. Okay, and the matrix itself, you can see the similar thing of leaving along the diagonal at some minus rate until you get to the absorption row. And then you've also got the 1 minus some probability times that rate for going to those other to the next state in the sequence, or with the corresponding amount of total rate of going to the absorption state. So there's kind of at each node, a conservation of total rate, but some of that rate goes on to the next node, and some of that leaves the system. Okay, so let's throw that distribution in there. Oh, is that still the same as before? I might have messed up going HG with that last one. Let's take a step back to the hyper-Erlang again and just plot that just to make sure. There we go. That's a very different distribution. My apologies. So yeah, this is more like a gamma. And actually, I like that this came about because it highlights something, which is one of the things that the pure mixtures of exponentials has is that you'll get something that usually looks very much like an exponential, but as soon as you start adding stuff like an Erlang, you'll often get some kind of unimodality. Usually. I think it may technically depend on the parameters, but this is more common to see once you have something Erlang built into the mix here. Okay, let's get back to Cox's distribution. We did define it, right? Yes, we did. Okay. let's use it and make sure we actually use the right distribution. And let's plot it. So this is kind of an unusual L-shaped, but it's also not quite as long-tailed as some of the other ones we've seen. And that's possibly because there's greater failure rates earlier. There's kind of this accumulating failure rate of can you get to the end of the gauntlet. It's not super surprising, but I also wouldn't have guessed this specifically ahead of time. Okay, so anyway, that's a walkthrough of some different particular special cases of phase-type distributions, but to give the summary points here is that phase-type distributions are a pretty general way of sampling the amount of time that some unit of flow stays inside of one of these absorbing Markov chains, which is one of the ways that we can say here is a set of states and that something is going through those states. Now remember, to take another step back out, because we've been talking about this probability distribution, where do probability distributions actually show up in the QPython package? The first main two ways, the two ways that we've covered so far, is to be used as arrival distributions, and the other one is to be used as service time distributions. Well, how does that work? Like, why would we do that? In the case of arrival distributions, maybe we know that there is some latent network of states that patients or customers or whatever have to go through before they even show up at your queuing node, and you want to represent that. These are not queuing node states that you're using in the phase type distribution necessarily. Sometimes they could be, but the point is you want to have some kind of network that some of states that something goes through, and you just want to account for the amount of time it takes to get through that network of states, even before a patient, customer, whatever, shows up at the first queuing node. The same thing as you're probably guessing at this point for the service time distributions is to say, what if the service itself is kind of complicated? The patient, customer, whatever, has to go through a bunch of different processing steps, but it's not necessarily the same set of processing steps every time, or in some cases with the Erlang, maybe it is. But the point there being that you can have these more complicated distributions for how long it takes to see the next arrival into a system because of some latent states, or because of how long the service itself takes. So hopefully that gives you some insight into more sophisticated distributions with Q. This can be combined with other kinds of customizations, like if you want to generalize beyond phase type distributions or use distributions that also involve network flow like this, but are not the phase type. That's also possible with the previous video where we covered custom probability distributions. Anyway, that's probably enough about probability distributions for one day. This video is getting a little bit long, so I will catch you in the next video and have a great day. Take care.